So welcome. Tonight's topic is recent observations require explanations. And how this came about is I started doing some reviewing of all the farthest, biggest, brightest stuff that we're finding lately. And went, wait a minute, that's bigger or brighter or farther than we're supposed to have according to models that we've tried and trusted for many, many years. And it turns out they're exceeding the models, but nobody's pointing out that they're exceeding the models. They're going, oh, that's an outlier. And then when the outlier gets peer reviewed, they went, well, we didn't observe it, or we're not going to include it in our research paper because it doesn't fit the model. Yeah, because the model is so well respected, nobody wants to question it. So tonight we'll talk about models and the recent peer-reviewed confirmed observations that don't fit the models. So I likened it to a square peg being fit into a round hole. Here's an example. If you see, there's lots in that graph at the bottom, there's lots of things that dip down below that red line. That red line is the mean. But if that were really the true mathematical mean of this data, then the line would have downward dips in it. It wouldn't go across the top of the gaps. And these two very tall spikes would have bent the graph upward. But what they're actually doing is they're saying, they don't fit the model, so we'll just exclude them from our research paper. That's not science, folks. There are other statistical models involving probabilities, averages, and weighted averages that they could still use. It'd show little curves in it. It wouldn't be quite the smooth line that they're showing there, but at least it would start to include some of this data that they're basically just dropping on the floor. And this is peer-reviewed data. So for those that don't follow the scientific method, it starts at the top where somebody goes, hey, look what I just saw. Well, why is that what you just saw? Is it bright, big, far, near, whatever? So you made an observation and you come up with a postulation as to why might it be that. So you do some research, you gather some other observations, you come up with a hypothesis, you test your experimental data, you analyze it, you offer other people to peer review it, or second set of eyes kind of things. And then when you think you got a good beat on things, you report your conclusion. And then a week later, somebody comes out with another observation that your conclusion is no longer valid. Well, that was the biggest of that thing that we saw up until the guy saw the next bigger thing. But they don't like saying that. They'll just say, this is the farthest, biggest, brightest, most energy output thing possible. And somebody over in the corner will go, but you peer reviewed my observation. Why didn't that change the model? Don't you understand how long we've had this model? It's a really good model. How is it a good model when the current observations based upon current technology and our more frequent observations basically just blow the model away? But you gotta understand who created the model. A noteworthy scientist, 50 years ago when we didn't have this technology said, this is the biggest it could ever be. So we'll take him at his word. Well, no, as soon as you have observations that are confirmed that blow away that limit, you should go back and revisit the model. But from what I found, they aren't revisiting the models. They're just saying, that's an outlier, but it's a peer-reviewed outlier. Well, we'll wait until somebody else has the same observation. Somebody at a different observatory has the same observation. Why aren't you changing the model? Because models are tough. So what's the smallest black hole? Well, he said that anything smaller than 3 solar masses, and a solar mass is the mass of our sun. So any black hole that is smaller than 3 times the mass of our sun probably wouldn't hold together and would be a neutron star or a white dwarf, certainly not a black hole. And we've now found one that's precisely 3 solar masses, because if it was less than that, it shouldn't be a black hole, but it is. multiple observations confirm it. So they're calling this one that's like dead on the money, 3 solar masses, as unicorn, because it's so rare, right up until they find another one that's like 2.8 solar masses. But now they've taken it to the extreme and said, well, depending upon what the circumstances are, you can have micro singularities. So they've now got black holes that are microscopic in size. So the whole model thing, just ignore the model. You can have black holes any size you want. But you were standing on that plateau of 3 solar masses for how many years? And it was really great. And then you found that, well, black holes can be much smaller than that. That's what I'm talking about, is the more we observe, the better the instruments we observe by, the more we find that some of these limits, some of these models that say, this is the smallest possible, the biggest possible, the brightest possible, they're no longer holding water, but we still quote them. This one's fun. We've seen the smallest black hole. What's the largest black hole? Well, anything larger than 10 billion solar masses wouldn't hold together, because the outer limits of the black hole would not have the sustainable gravity to keep the accretion disk going, and it would kind of fall apart into maybe multiple black holes. And they said that about something called TON 618. If you recognize the nomenclature, TON 618 was not originally believed to be a black hole. It was believed to be a globular cluster on the outskirts of our galaxy. And then they went and did more observations. They found out, yep, it's a black hole. But no black holes will be bigger than that. And then they went out and found Phoenix A, which is several times larger than TON 618. Like, so what's the upper limit on a black hole again? Yeah, you shouldn't have one right now, because you keep finding bigger ones. So in case you're curious about TON 618 itself, if it were visible light that it was putting out of its particular wavelengths, it would be magnitude minus 30. That's really, really bright. But how bright is bright? Oh, that's super luminous. But maybe hyperluminous. How many more superlatives do you have for describing it's bigger than we thought it would ever be? Oh, yeah, okay. So if we were closer to TON 618, our goose would be cooked. Luckily, it's 10.5 billion light years away. So even though it's a black hole and it's putting out lots of energy, we're fine. Now, it's a black hole without an accretion disk at the moment, because it's not feeding. And if it were feeding, we'd call it a quasar. But how did you get something this big? Oh, it must be really, really old, part of the original universe. It was a direct collapse. You got any data to prove that? No, but we have a postulation. Oh, no theory, just a postulation. So, yeah. Hold them accountable to the same level that they would want to hold you accountable had you postulated something. What's the largest possible terrestrial planet? The Earth is a terrestrial or rocky planet. What's the largest possible rocky planet? Well, they used to say 2 Earth masses. It's a so-called super Earth. Well, turns out there's an exoplanet out there that's 5 Earth masses, called Gliese 436c. And they've confirmed its presence as an exoplanet. But nothing's going to be bigger than that. 5 Earth masses is, and if you talk to recent graduates, they'll tell you, actually, it's 10 Earth masses, because that's just what they're looking at right now. And 10 is a really nice round number. Where'd they get the 10 from? I think they grabbed the 10 from a dark odoriferous place, basically, behind themselves. But if 2 is where you're at now with the model, and you know you've got a 5, a 10 will kick the can down the road. But nobody's saying stop using that model of 2, because 2 is definitely not the biggest. So an interesting side note here is that the larger terrestrial planets would have a difficult time with rocket propulsion. if you were on a planet that was 6.5 times the mass of the Earth, chemical-based rocket propulsion wouldn't work. You could never develop sufficient thrust for the mass of your launch vehicle and its fuel tanks using the chemistry that we know today to get it to lift off the ground to get it to orbit. So if there are extraterrestrial aliens out there and they happen to live on a super Earth that's 5 or 6 times the size of the Earth, they're never going to come see us, and we're never going to land there because current chemical propulsion won't let it happen. Just an interesting thing. When people are talking about, we're never going to visit because of the speed of light, well, there's another boundary called mass. Okay, that's terrestrial planets. What about the largest gaseous planet? Well, the largest gaseous planet would be 80 times the mass of Jupiter. What happened to those stars? So if something is big enough to be 80 times the mass of Jupiter, why is it not a star? Well, we know that stars are, brown dwarfs are only 13 times the mass of Jupiter. Well, it turns out it's the chemistry of the star that dictates whether it's going to be a large gaseous planet or a brown dwarf. Hydrogen is easy to fuse. Helium is still easy to fuse. When you get to large gaseous planets that have predominantly nitrogen compounds or carbon compounds like ammonia or methane, it's really hard to get enough gravity to compress that to create fusion to ignite it as a star. So you can have a gaseous planet that's bigger than the smallest star, which is kind of an irony for the two models of what's the biggest gaseous planet and what's the smallest star. This one I found interesting as well, that they talk about what kinds of stars, what temperatures of stars are the population, how many different kinds of stars, and then of those stars, which of them contain like metals. Metals can include things like calcium too, but which of them predominantly have a lot of metal? And there is this age-old boundary of the Eddington limit. The same Eddington that was talking about, solar eclipses with Einstein. So Eddington came up with this formulation, and you can see the dotted line there of, this is the population of star types that ought to exist. And if you look, all those little blue and red dots are down low towards the right. They're well below the Eddington formula. Why are people still quoting it? And if you look at the little plus signs, there's a lot of plus signs out there that are blue. The plus signs that are red are the metal poor stars. The red dots are the metal poor stars. But the blue ones are the dominant ones and are metal rich. And there seems to be a lot of metal rich stars of dense population of K type. Our sun is a G type. G2, that's that red vertical line you see just past the G. But apparently there's a lot more K-type stars out there, which are, think of them as orange stars, that are stable. In fact, they're billions of years more stable than our sun before you get to those red dwarfs off on the right. So star populations, not what we think they are. What's the largest possible star? And they talk about the largest one, according to the formula, as being 1,500 times the radius of our sun. They've got multiple confirmed observations that go all the way up to 2,150 times our sun. Well, they're calling those quasi-stars. They don't know quite what they are, but they're still calling them stars. Yeah. So they've broadened the limit up to 3.3 times that 1,500 to maybe get some headroom. So if they find bigger and bigger stars, they still fit within the original formula. They just changed the number. How about energy burst? They always talk about, well, that supernova, when it happened, was how many stellar masses worth of energy? How much radiation came out of that? How strong was the gamma ray burst? And they found what they call the BOAT, the biggest of all time, basically the biggest they've seen so far. It was so bright in gamma that it saturated the gamma ray sensor of the Fermi Gamma Ray Space Telescope. So they looked at it in X-ray. And if you look at the reddish one, the bullseye looking one, it's white in the center. That's because not only did it saturate the gamma ray detector of one satellite, it saturated the X-ray detector of another satellite. That is a lot of energy. So that's the biggest of all time. But it saturated the sensor. So there's no room left in our instruments to find anything brighter. We're going to have to build instruments that have more headroom in them. So that's the energy output. But let's talk about the total amount of energy you would expect to come, not from the object itself, but even from the accretion disk and all the distribution of the light coming from that. They're now talking about superluminal or hyperluminal quasars, because it's not just the black hole of the quasar itself, it's the accretion disk and a sphere of excited gas around it. So we're talking about infrared, ultraviolet, X-ray, gamma, just the total collection of that. But they're leaving out gravity waves because we have no sensors to detect the low amplitude, high frequency gravity waves just yet. We will sometime. Yes.
Sorry to interrupt. The picture that's displayed there on this screen is a artistic view, right?
Yes, it is.
Thank you.
Yeah, but the amount of energy coming out of it is more than can be held in the electromagnetic spectrum. We look at all the wavelengths, there's energy in all of them. And this is the brightest things that they've ever talked about. So they're leaving out gravity waves. Well, we know when, black holes collide and quasars and neutron stars collide, you get gravity waves. The gravity waves are another form of expressing energy output because the electromagnetic spectrum just can't hold it. So why are we not including gravity waves? Well, because our models don't account for gravity waves and our instruments can't see currently. They're blind to the low amplitude, high frequency gravity waves, although they're improving them. So they go back to the, Eddington model and such, and it just doesn't fit. But I did find an actual presentation from 2022 where somebody described their model as close to the best possible accuracy. That doesn't mean it has the best accuracy. It's what we got. But they're basically saying we're finding data that doesn't fit the model. It exceeds the model. So now they're talking even more luminous. This is a new term that I had found is now we're talking about something that's 1 million times the gamma ray burst that we've seen, but it's 10 million years out there, 10 million light years out there. So what would you call that more than hyperluminous thing? They're calling them quasar tsunamis, for want of a better word. They've run out of superlatives. Not super duper ultra mega hyper, but it's now called a quasar tsunami. And I saw 7 papers on it, 5 of which covered quasars as being quasar tsunamis and no mention of gravity wave emissions because they don't fit the models and we don't have the instruments to measure it. So just look the other way. But you're postulating, you're coming up with a theory. Why don't you include that, even though you can't currently measure it? Because it doesn't fit the model. And we were talking about rogues earlier. Rogues are things that don't fit models big time. So if you have a moon that's cast out from a planet, that's a moon that is no longer orbiting a planet. So it doesn't fit the model of what is a moon. Well, a moon is something that orbits a planet. Well, what if it's a rogue moon? It's no longer orbiting a planet. What about a planet? You've got a planet that gets kicked out of a solar system. It's no longer orbiting its parent star, but you're still calling it a planet. But planets are supposed to orbit stars. Well, it's a rogue planet. What about stars that get kicked out? Well, they're supposed to orbit in the arms of galaxies, but it's a rogue star. Same thing about supermassive black holes. They're supposed to be at the centers of galaxies, but now we've got rogue supermassive black holes. And galaxies are supposed to merge, just, like Andromeda and Milky Way are going to come together. They don't orbit one another. Well, as we look at things more often, we see that they are moving with very small vectors, not orbiting how we think they are. There are stars like Barnard's star. It has a very large angular velocity, which means it's moving across the sky. And in 10 years, with an amateur telescope, you can actually see where it was and where it is. So it's moving pretty fast, but it's moving fast laterally across us. So what about, we even have asteroids that have, just passerby. They're going through our solar system. Oumuamua. Where did it come from? Where is it heading to? It's just a visitor. We've got asteroids in the asteroid belt that have their own moons, but I thought it was a planet that had moons. No, we've got asteroids that have moons. We sent one to, Didymos, and we sent a probe to Didymos that's orbiting Dimorphos. So yeah, we've actually done that without saying, oh, by the way, this is not a planet and it's got a moon orbiting it. So yeah, just the models are what the models are. And it gets to a big size. People will talk about Andromeda and Milky Way merging, and they will in 1 billion years or so. But how many people knew that we're part of a galactic cluster, a supergalactic cluster, that's part of an even greater galactic cluster, and we're all moving towards something called the Great Attractor, which is a even more super cluster. And they found out that there's an even bigger cluster, that if you measure all the movement vectors, you can see that there's a Vela galactic supercluster. But you already called something a supercluster. Is this an ultra mega super duper cluster? You ran out of superlatives. And how is it that all these things are moving? What are all these vectors? Is it just gravity? So they come up with dark energy and dark matter. But there are other fringe things that they talk about, like the Hubble flow and the dark flow, that one's pulling and the other's pushing. And the one that's even better is, and this is straight from Men in Black, the dipole repeller. Like, if you can't explain it as being attracted to something by gravity, is it being pushed? What is that pushing force? It's the dipole repeller, not to be confused with the expansion of the universe. So as we see more and more, and we map more and more of the movements, we find that there are bigger and bigger structures that we're a part of. That's a very, very small part. Currently, the largest structure known in the universe is 10 billion light years across, or 120 degrees of sky. This structure occupies basically 10% of the known universe. Now, what would cause a structure this large to exist? And there are no postulations, although I have one. Back when the universe was formed, this was resulting from a squirt of quarks, like a fire hose of quarks that eventually stabilized down, but they're all still moving with that original momentum it had. And as they interact with each other, it becomes like a meandering river. So when somebody says, we know what the largest structure is, we don't. Well, what's holding these structures together? The dark matter, dark energy, gravity, pick one. But yeah, and it turns out that this structure is actually moving towards something that we have identified as the Hercules-Corona, Corona Borealis Great Wall. And nobody wants to claim that this is the outer edge of the universe, but it's as far as we can see structure. So it's time to rethink what's too far and what size is the biggest structure. And as my closing argument, I offer the latest video from Dr. Becky. She's a recent astrophysicist, PhD graduate. She's a research fellow at the Royal Astronomical Society at the University of Oxford. So she knows a thing or two about cosmology and black holes and has written books on them. And I was very pleased that she came out this week and basically blew away the smoke and mirrors and said, you know, there's things we don't know about in the universe. And some of these things don't fit our models because the models may not be right. So the Lambda CDM and the IMF are two astrophysicists' respected models, and we're now finding observations that don't fit the models. And why would that be? Well, turns out when you're examining things with instruments, the instruments convert certain wavelengths into electrical voltage, and you measure the voltage, but it's not a continuous curve. So if something happens to occur between your samples, because you're not sampling continuously wide enough or fast enough, you have gaps in your observation. And if something falls in the gaps, you may not see it until the next better instrument comes out, and all of a sudden you've got something you didn't see before. It's not because it didn't exist before, it's because you were blind to it. So yeah, I was very happy to see that, yep, we got a good beat on things. Nope. Do we know what we know? Yes. Is there more for us to know? Yes. So just think of it as all those long-standing models from certainly the late 1800s into the mid 1900s, before we had the instrumentation technology that we do now. Look for them to, hopefully within the next 10 years or so, start reevaluating them as maybe we need a new model. In conclusion, as your technology observes and you observe more often, you're going to see things that are above and below the limits that you used to have. So if the models were based upon those old limits and you have new limits, time to look at the model. Don't just exclude things from your model because it doesn't fit. Or as I like to say, there are scary sayings that well-known scientists in research programs don't want to say. You know, things go bump in the night. This is a dream to some and a nightmare to others. There are stranger things in heaven and earth than thought of in your philosophies, Shakespeare. Or the one I like, you'll never know how much you didn't know until you know what you didn't know. Or promote models, but you know, if you're promoting a model that you know is inaccurate or lacks completeness, do state that in your research paper, like, here's what we looked at, here's all the wavelengths we looked at, here's the gaps we didn't see, here's the observations we didn't make, and we're aware that newer observations may come along that might exceed this model, but this is the best we got now. And I'm fine with that, but just be willing to admit that. Don't just kind of look the other way. Or as I like to say, pastime to broaden our minds, as Jack Nicholson would say in the Michael Keaton Batman movie. Okay. I cranked it in there in 25 minutes. Lots of research work. Okay. Hey, no mathematical formulas, no sophisticated geometries.
I like formulas.
And you did have a graph.
I did have two charts. I had the one of the very first one where things don't fit, you know, the square peg doesn't fit in the round hole, the chart at the bottom. And then later on, I had the chart of maximum gaseous planet size based upon density. And all these things were like, how come they're scattered above and below the line? Because the model's wrong. And then the other one, which was, well, you know, sizes of things, what's the maximum luminosity and such. Yeah, there's plenty of data out there. And if you look at the data, you go, why for are you ignoring all your data points? Because they make our model look bad? Maybe you should look at your model.
How come the model can use calcium as an iron?
Calcium is not an iron. Calcium is a metal. You have to look on.
Okay, I meant a metal. That's what I
Okay,
meant. I'm
on
sorry. But you said they used it as a metal. You said calcium could be used as a metal.
If you're looking,
No, that it's a misnomer. It's because in astronomy, everything above hydrogen and helium we call metal.
I was going to say, if you look at the periodic table of elements, there is a section that are noble gases, and there's a section over more towards the right that are all called metals. And if you're looking at the spectrographic image of a star, and you want to find out what the level of fusion is going on in the star, if you find more than just helium and hydrogen, you start finding metals that can include things like calcium. You start finding those, you know what the star is burning. You know it's not a brand new star, it's a little older star. So that's why they look for metallicity in stars, is to know basically how far along are they.
So it isn't like calcium is attached to some kind of metal. It's
No, if you see
calcium in and of itself, they call a metal.
it's called
Yeah, and
metallic.
then you call it that way because when you get atmosphere of stars, everything is ionized. So you're not going to find something like a salt. You're going to find just a metal on one side and some ion of other kinds of things in the other side. But in astronomy, when you say metallicity, it means that's something that's a little bit older. So you find like globular clusters, they have very little things above hydrogen and helium. So we call it low metallicity. So what it means that those objects were made, closer to the time of the right after the Big Bang, like the first reionization of the universe. Now, if you find something that contemporaneous with us, then those objects have high metallicity, so they have all the elements of the periodic table, and then in that case we say the high metallicity, and as everything that you find in the periodic table above hydrogen and helium.
Yeah, and what they're finding in the large survey observations is there are a lot more orange stars in the mid-range that are high metallicity stars. So these are very old, stable orange stars, which means any planets that are orbiting them are likely to be 1 billion plus years older than Earth. So if you're looking for a civilization that is more advanced than us, that might have cracked the secret of speed of light, that they're probably going to be on planets orbiting those orange stars, and there's plenty of them. There's more than they originally thought. If you remember back to the early days of the Kepler mission, when they were looking for exoplanets, they initially started looking at only G2 type stars, sun type stars.
You cracked it, Monroe. That's why they have gray skin.
Right. Well, they're now finding out that, at the end of the Kepler mission, on the K2 mission, they said, why don't we look at some of the other kinds of stars instead of the sun-like ones? And they found a huge quantity of orange stars that had planets around them. And they're finding those are high metallicity stars, which means they're 1 billion years older than our sun. So if they have planets, those are planets that could conceivably be many millions to upwards of 1 billion years more advanced than us. So,
on that graph, the orange was representing suns, but what was the blue representing?
Stars, just
Stars?
not like they're higher temperature, lower metallicity stars.
And what were you supposed to get out of that graph? I'm thinking.
Okay, the thing to make out of that was,
it wasn't fitting a model. It wasn't fitting the guy's model that you had the name on the top on the left.
Eddington, yeah. Yeah, let me go back to it.
So it wasn't fitting his model, and that's why you were.
Yeah, that's why I was pointing it out. Is Eddington came up with this model of population densities, and he said this ought to be the line that all the stars in our galaxy should fall into. Now, also remember that Eddington was in the early 1900s back when we thought that it was the Andromeda Nebula, not the Andromeda Galaxy. So the only galaxy he had to measure was Milky Way. And the only stars he could see were the ones he wasn't using an infrared space telescope to see. So,
And he thought that the Milky Way was the only one, right?
yeah, we were the only galaxy out there. Everything else was
Right.
just a nebula. Well, when you have a limited observation set, you can create a model that doesn't match the eventual reality that you observe. And that's what happened. But they're still quoting the Eddington model. It was on their graph. Look, here's the Eddington model. By the
Was
way,
it helpful? Was the Eddington model helpful originally?
originally it was helpful in qualifying what the Harvard calculators, what the Harvard computers were seeing. These were the women that were categorizing stars. That's where you get your codes across the top. They were categorizing the stars by their brightness and their color. But so that's all the data they had to work with. And most of that data did follow along Eddington's plot. But as we've started to observe with better observatories, better instrument technology, more frequent observations in different wavelengths, we're finding, there's a lot more stars over towards K. And a lot of those stars are high metallicity stars. And we wouldn't know that, but we have better spectroscopic instruments now. We've got kind of the stuff that was on Spitzer Space Telescope, which was infrared. Well, we've got the James Webb Space Telescope, which is also infrared. And these things have very good, not only imagers, but spectroscopic analysis.
So
So
his
the finding-
original information was good for what we had at that time. And when we got this other information that
It
came,
is a baseline where you start your studies and then you aggregate the data and you change the model.
right.
the
I'm just
problem they have
asking,
is they're not changing the models.
my question is his information that he gave originally for that slim part that you
Mhm.
said was helpful, is it still helpful? Maybe that's why they still
No.
use it, if it's still
No.
helpful. Or do they have to wipe everything out, say, oh, your model didn't work? It
No,
may have
no.
been
So,
helpful for that, but it didn't work.
They started with the Eddington model, and then you see the L shape that you see at the position of stars and those letters. That became the Hertzsprung-Russell model because the
Right.
Eddington model didn't fit anymore. So they stopped using, and now that's the Hertzsprung-Russell model that every student of astronomy uses. And
This is the
even
one that we're
without
seeing, that we're
rewriting, just
looking at?
looking at the shape of the model, you can recognize it because you know the position of stars.
That's what we're looking at right now.
Right. But not exactly, because this is newer data. This is data from 2012 onward. The HR Hertzsprung-Russell is actually, if you start from the left side and you go to where that big red dot is in the center, and then you go up to the right, that's the HR curve. But what's this stuff going down towards the lower right?
Yeah.
Well, even HR is only going to be good.
Yeah, but the
Right.
Monroe, that's the exact shape of the Hertzsprung-Russell. It's just that this is, well, it's normalized. Oh, it's log of G dex. Yeah.
Hmm.
But it is hard for, it's like, even to start being writing just for the shape of it, and then when I look at the top and the bottom, oh, that's hard for Hertzsprung-Russell model.
Yeah, because we
It's
move.
like every student of astronomy can recognize those shapes.
And back when Eddington was around, everybody recognized his shape. My point is, when you have observations that don't fit models, it's time to work with a different model. We
Yeah,
went from
so that
Eddington
you
to
see the
So are you
HR.
change
saying
from one
they
to the
need a
other.
different model than what we have here?
No, we're using you see the shape of stars, the model that we use, the normalized to the 10 log of the distances of stars. So you compare, like if artificially you put all the stars in the same distances and you make a graph and you know how many of the large stars are there and what's the phase of the star life in the galaxy, so you end up having the same shape in the galaxy. You look at it, it follows, and that's what we call it nowadays. That shape that you see all the color stars close together, that is what the gave origin to the Hertzsprung-Russell model.
The HR model is what we have today. The Eddington model is what we had in the early 1900s.
And tomorrow?
Don't count HR to last forever.
Okay.
HR is just what we have today. We are finding observations that are on the edge of HR. We're finding a lot more K than we originally thought. So
That's where most of the stars are at, right?
yeah, it looks like more and more stars are being found class K, and they're being found high metallicity. So yeah, HR is good today. They're being taught HR today, but don't think of it as God's gift to models and will be around forever. It's just what we have today. And that's the whole point, is when your observations exceed your model, time to come up with a new model.
But like a lot of times when you say, when we're looking at things, that this isn't actually today what we're seeing, like when we see the stars outside, those stars are set from thousands of millions of years ago or something. So
Yes.
This is going to be the same thing here, right?
No, these are stars in our galaxy, so they might be a few million years old at most.
So it won't be that old, but they're older than what we're seeing.
They're not billions of years old. They're maybe millions of years old.
Okay.
But if they're K-type stars, that's another question, is if they're K-type, they could be a billion years old. And I'm sorry, the Milky Way isn't a billion years across. Maybe when were they formed? We may have to investigate that model as well. We only work from what we know today, and we only work with the models that are created from the data we have today. As we find new data, we should change the models. I think we're sticking with models for their name noteworthiness. If Einstein came up with a model, that's the end of it. He came up with a model, nobody can. Okay. And then there's
this was a good example of when they did change a model. I mean, you showed a good example that they changed a model, and now they have this model, and you're saying they need to open up and think about
really a
changing
model
it again?
that became a model, but this coming from observation. This graph, the data is empirical because they actually look at the stars, they calculate the temperatures, and they classify them, and that's the shape they hold is what it is, an observation. So this is totally empirical.
Yep.
So it's a good example of what you're looking at?
A model is created from the data you have. So if you've got several points along a curve, you can fit your model to match the data. But if you wanted to say, I'm going to come up with a model that will create an equation that fits anywhere on the curve, you may have observations, empirical evidence that don't match your model, in which case you might want to reevaluate your model. And if you're not a noteworthy scientist, they'll kick your model to the curb and tell you go back and do your homework again. If you're a noteworthy scientist and you have a Nobel Prize for it, it's like, tread lightly on his model. I think that we probably are giving them too much the benefit of the doubt, especially when you've got observations that your instruments can't detect, like low amplitude, high frequency gravity waves. And it's just like, I don't see it. I can't see it. I can't observe it. Therefore, it doesn't exist. Well, the rest of your stuff in your model is postulated.
So am I right that you like this graph, or you don't like it? You think that this graph is going to change? Not that you don't like it.
It's not that I don't like it. I don't like the fact that the Eddington line is in there, because it doesn't carry any weight anymore, because all those red and blue dots are real world data. That's closely aligned with the Hertzsprung-Russell diagram. So I'm fine with that. But I also realize that's just today. And as we've got more and more instruments looking more often at more things, in different spectra, maybe we're going to find that there's a lot more K out there than we thought. So that big clump down near the big red dot may move up to the right. So when you look at something, you look at a presentation of data, or you look at a model, realize that's what they had to work with. That's what they were working with today. That's what we have today. It may change tomorrow, but what you should be on the lookout for is, what did this ignore? What data points did they sort of sit by the wayside because they didn't match? They didn't fit the model, therefore we ignored them. Don't ever do that. If they're peer-reviewed, if they're confirmed by multiple observations, they're real data. If your model doesn't accommodate that data, maybe there's some review work you need on your model. That's all I'm saying.
So was Eddington the guy who proved Einstein's special relativity with the eclipse thing?
He wasn't the guy that proved it. He was the guy that gathered the observations to allow Einstein to prove it.
Oh, okay. Well, so he was still okay.
Yeah,
Even if his limit isn't right.
I think he was a great scientist, a great observer. He made a lot of data logs, and from what he had, he said, this is where the population should be. And then we found out later from observations, the population should be this. And we have the HR diagram that matches more or less that curve. But we're now starting to observe even more stars with like Gaia. And there'll be more Ks out there. And the metallicity is higher. So these are much older stars.
So if the metallicity is higher, does it I mean,
It means that the populations are younger.
Okay, so exactly. So if the right, if on the one hand we're seeing how wide the galaxy is, and if that presents a contradiction to the original theory for how long the stellar evolution takes place, then right. So if the stars are younger.
No, not that the stars is younger. The formation of those stars is more recent. So I don't know. Let me see if I can get an explanation. So imagine that right after the Big Bang, all you had was hydrogen and helium. So we call this population. They're very, very old. They are very poor metal. They only have hydrogen and helium, and they have a different lifespan, because when you have all the elements in the atmospheres of the stars, the processes occur a little bit faster, because there is all the cycles that help the fusion. So you have population 3 of stars. That's the ones that form close to the Big Bang. The population 2 and population 1, the ones that close to us in age, they are having more metals. So calculating that, you can have an idea that they form a little bit closer to us in age. But for you to have stars that are having enough silicates to make planets, to make solid objects, to have dust, to have, more massive stuff in their disks to form, you need younger stars that have more metals. So that's how you calculate, how the age of some of those stars. You can calculate what kind of metals they have in their atmosphere, and if they are population 1, 2, or 3, or maybe, more. I don't know if I clarify anything.
Yeah, that makes perfect sense. You're saying that younger stars were formed from a third generation that have more metal because they were formed from other stars that were formed from stars that originally had less metal, because first they had hydrogen, then they had hydrogen and helium, then they had hydrogen and helium and lithium and carbon, and now they have metals because it's the third one. Sure, that's clear. I think that's what you said.
You got it.
But,
you got it. You got it. You understood.
Yeah. So the question is then, if the stars are younger than we thought, the high metallicity stars, are we thinking that the universe is younger as well, or that
No,
just the
no.
distribution of the
It's just
time
the
in which the
distribution of
stars were
stars.
created?
No.
It's just the we are finding smaller stars because now you have better glasses.
Yeah.
So
Because there are an awful
whatever is
lot of
smaller,
clocks, right?
yeah. So not that we are changing completely the model, we are populating the model better because now we have more points of data.
Right. But the other thing is that we are finding galaxies that their age doesn't match where we think their age should be. So I purposely left that out because that's the discussion that I'm queuing up. I need to get more data from a couple of astrophysicists as to what their call is on why these outliers for energy output and age of galaxies would say they're much farther away, much older than we think they should be. So, yep, there's models out there that we're now observing things that don't fit the models, and they're not quite ready to change the models, but the observations are still there. And some of those newest observations come from the James Webb Space Telescope. How can you find a galaxy that's supposedly 19 billion like 19 billion years old? That's supposedly not possible. So they're trying to find, well, maybe it's an observational error. We haven't got any other telescopes that can confirm it because the newest, hottest, best thing we have is the Webb. So we may have to wait until a next generation telescope goes out there to, get a second set of eyes on the same galaxy. And then that one, we're going to find new stuff. And then we're going to have to wait for even the next generation to find better. But by the time we start finding better on top of better, the plural HR diagram may be long in the tooth, and the curve might be a little different shaped.
But we still know fundamentally when we were fused, because we know how much U-235 there is, how many byproducts there are. So all we need to do is reshape the model around us or around what we know about the atomic clocks.
Yes, but if we go one generation prior to our sun, the picture is more vague. So we know our star is not a first generation star. Ours is at least a third generation star, but we don't know if it's a fourth generation star or not.
Right.
There's a little thing called, what did they call it? Hell, lithium-8. It's the quantity of lithium-8 that you look for that tells you how late in the generation your particular generation star is.
Yeah, it depends also the temperature, because depending on the we do that for planets, like massive planets, because then we can see they actually fuse lithium if they have left over from the universe. So you can date some galaxies using that. You can, that is quite a few that is a good presentation to do, Monroe. You can number the things that you can see the distances, and also the things that we use to date things. So how far that is, how fast it's moving away from us, what kind of profile that you look in the temperature of the stars, so you know what kind of elements should be fusing or should be ceased to exist, or what kind of ionization you get depending how old those stars are. There is like quite a few ways for you to do that, and then you can like make a presentation just to how far things are and how do you know that, and how old things are and how do you know that.
And in those particular calculations, our instruments are kind of our weak link. So whatever numbers they're coming out with, they could be off by 10 or 15%, and everybody agrees that's okay. 10, 15% is fine. So when you hear somebody say, it's 10 billion years old, and somebody says plus or minus 1 billion, that's fine.
That's fine, yeah.
It shouldn't be 10 billion years plus or minus 10 billion years.
When you measure things in millions of years, if you're wrong by, you know, a couple of hundreds of thousands of years, your measurement's still quite precise. And
If-
then when you measure things in billions of years, 100 million years in error, it's not bad at all.
Right. What you don't want to have happen is it's not off by plus or minus 10 or 15%. It's off by several times, because when you get to have something that's, well, it's plus or minus 200%, like, go back and do your work again. You know, acknowledge that your value is off. When you're studying the mathematical precision of observations, metrology, not meteorology, but metrology, when you see these scientific research observations and you see something's out to like 7 decimal places, and you've got 2 different observations and they're both the same to 7 decimal places, but out at 9 decimal places, each observation's like off by 2. That's fine, that's acceptable, but it shouldn't be, you know, fewer digits than that. You should be able to work within the tolerance of whatever the physics is of the materials you use to gather the data, and most of it is from analog to digital conversion, so it's a matter of photons encountering metals and the metals producing electrons, and you're counting the electrons, because that's how we measure everything. Okay. We're at 12:35. Anything else?
Yeah, can I ask you a question about time travel?
Yes, we like that.
You can ask, but I've got another presentation I'm working on regarding the Higgs field and the Higgs boson, and that does get into faster than light, but sure, go ahead, ask.
Well, if it's more appropriate to answer after with that presentation, it'll be fine. It happens, I heard a short by Neil deGrasse Tyson. It could have been by anybody, but he happened to be saying it. And he was mentioning the movie Back to the Future. Was saying in the movie, it must have been, that should that really have happened, obviously you suspend disbelief. But he said, should that really have happened, it's awfully lucky that they timed it exactly on the year anniversary to the date and time and minute to when some other event happened, because the Earth would have been in a different place, right?
Yes.
And if you had it in a different place, you'd have wound up in empty space. But
Yes.
in fact, what you're telling me, well, not yet, what you were discussing tonight is just what I was thinking of when he said that actually that may be true with respect to the rotation of the Earth with respect to the sun for the minute.
Absolutely.
And it may be true with respect to where the Earth is around the sun, but
Yes.
that doesn't take into account where the sun is with respect to the galactic center, or where the galaxy is in the galactic cluster. So
Yeah.
with respect to time travel, what is it relative to? How do you wind up in, aren't you going to always wind up in the middle of interstellar space?
No, the way I describe it is, if you want to travel in space at high speed, you will be traveling in time. If you want to travel in time, you must first master traveling through space with a high precision and high speed. So yes, the old time machine movie, the original one, where they put a cigar in the little time machine and then they send it on its way, and then like a year later the little time machine shows up in the same laboratory on the same table with the bent cigar in it. Like, that would never happen, because when you travel through time, you also travel through space. Otherwise, you don't wind up where you think you are. You will be out in open space. Basically, it went on its merry way beneath you. And if you leave here and come back to physically the same spot, but at a future time, the Earth won't be there. So time and relative dimensions in space.
Oh, that makes it a little bit harder problem. Thank you.
No, no,
If we're all moving at the same speed, like you're in an airplane and you throw a ball up and down, it travels with you. If you're just going, so the space is going to move along with the time.
but you're changing the space that you're in, because if you're going from current time to future time, that's future space as well. And they call it space time for a reason. You have to coordinate both of them at the same time.
Joe,
So if you want to travel in time, learn how to travel in space with high precision, high velocity first. If you want to travel in space, you can hang back on the dealing with time travel until you do things like put GPS satellites in orbit, and then you have to adjust the math a little bit.
I guess I'm going to have to recalibrate my flux capacitor.
Yes. Time travel is a lot more difficult, and it has nothing to do with the actual time travel. It has more to do with the space travel than it has to do with the time travel.
Because it's really space-time.
Correct. You're moving from one point in space-time to another point in space-time. Now, if it's a relatively short distance, like I'm moving from where my left finger is to 1 second later where my right finger is, what would be the problem? The Earth is rotating at over 1,000 miles an hour to the east. So as long as I move from south to north, I won't engage that. But if I move from east to west, yeah, I need to compensate for that rotation of the Earth. Because at 1,000 miles an hour, even 10 inches is going to be enough to affect where I'm going to wind up. Or how did I see it in the movie recently? It's complicated. It's complicated.
And I like the idea of space to travel just like a few minutes before, because there's a lot of times when I want to just take back something I said and change it just, 15 minutes ago. If you could do that, that would be great. Or 2 minutes ago, even you catch things.
In space, things are typically moving at the speed of light, barring the Higgs field. Imagine the Earth. It's rotating. It's going around the sun. Let's ignore the sun going through the galaxy at the moment and say the shortest distance between 2 points is a straight line.
Yes.
Therefore, the Earth going around the sun is almost circular, so it's not a straight line. But radio emanations coming off the Earth are traveling in a straight line. So as the Earth is going around a curve and radio emissions are a straight line, why is it that we can't receive radio transmissions that are from slightly in the future? Because they're going to be going a shorter distance in a straight line. What would be an interesting radio transmission that you'd like to hear an hour ahead in the future?
Horse races.
Well, you're close. You're close. The Florida
Lottery.
The Florida lottery, when they broadcast it on TV, you'd like to be on this Earth listening to the future Earth's broadcast of the lottery results, so then you could take advantage of it because you're an hour earlier.
So you didn't have to actually travel yourself.
No, all you had to do was pick up the electromagnetic emanations from the future Earth. So you don't have to travel in time to make a lot of money to then do whatever you want to learn how to travel in time. Got to get your foundational monies first.
Yeah, but the time the space-time police will catch you.
They're not the space-time police. Get it right. They're called time cops.
Oh yes, that's correct.
Yeah. Even in Doctor Who,
You
they
could
have
go back in
codes.
time and you could have said that correctly.
Well, my mind can go back in time because it has storage capacity. So I knew what a time
I'm
cup was.
cooked.
All right, then. Anything else before we close?